Hey everyone, welcome to this video, and today we are going to look under the surface of a time series database. First, let's try to understand what a time series database is. So we use a specific kind of database for handling data which comes across time. For example, price of a stock across some time. For each point in time, we have a value. You can see that this data has some common characteristics. The first one, obviously, is that time is the primary index. All the data, all the querying that we will do will be on time. For example, we can ask the stock price of HDFC from this date to this date, or we can ask the database that give me CPU usage of this node from this moment to this moment, right? Another characteristic that the data is mostly append only, right? Which means that you will be only mostly adding to the database and not going back and changing things and deleting things. I mean, it's a time series database, right? You cannot go and change the past. There will be some databases which will allow updates, but that is not expected to happen frequently. Same for deletes. Databases will allow deletes, but that will not be allowed very frequently, right? And also these two events will be much lesser compared to appends and writes. So our database has to be write heavy because the writes will be coming in very frequently, right? Now with this in mind, we need to think how to store and retrieve this data effectively. In this video, we will focus on the storage engine or the component in the database which handles the storage and retrieval of the data from the disk. The design I'm going to discuss today is from tsdb of Prometheus. This is like the embedded time series database storage engine that is used in Prometheus, which is a metrics collection and observability software, if you know about that. I'll also throw in some ideas from InfluxDB IOX, which is another new storage engine if some situation comes up like that. So this video owes its information from a few blog posts and one paper. I'll be linking those below. So let's come to our topic. Now, firstly, I want to say that many people get a bit intimidated when they hear jargon like storage engine and database internals, but stay with me. Taking things slowly, this is no rocket science. It might take a little bit to form the mental models to understand it, but that's normal. You can get it easily. Firstly, let's take a look on how time series data looks. So we will have a metric name and tags with it. Finally, we'll also have a timestamp and the value for that data point. Imagine we want to get the number of HTTP requests till now for an instance and for a particular path. So this metric name here is request total, and then we will pass the other parameters as tags. So the path is /status. For that HTTP path we want to get the data, or we want to store the data for that. The method is get, and the instance name for that particular node is this, right? And we will obviously give the timestamp and the value of the data, right? So this is how our data will look like, and this is the data how is stored in tsdb. And so we will go further with this, keeping this data model in mind, right? So a fundamental technique to make writes faster on disk is if you write data in batches and sequentially. So writing a 64 KB, a 64 KB piece of data on the disk at once is better than writing multiple 8 KB pieces of data across the disk. So in many write heavy databases, we first buffer the data somewhere in the memory, and then when it fills up, we flush it into the disk. So basically it's like a tap of water is opened and you collect the water in a bucket, and then you use that bucket to throw in a pool and fill a pool, right? It's a very bad analogy, but let's go with it, right? So we are doing something similar here. We are buffering all the data here, and then we are writing a lot of data at once. Not a lot of data, but comparatively a lot of data at once, right? So this end memory data structure in the case of tsdb is called the head, right? And whenever data is written in the database, it is first written in this in-memory data structure. But we cannot keep our data forever in here. So when it reaches a predefined time memory, let's say 2 hours worth of data, this would be flushed to the disk, and this will be called a block on the disk. Now, not only this way it helps our writes to be faster, but it is seen that time series databases, a vast majority of queries done are on the recent data, especially in case of metrics. Thus, if the most recent data is in the RAM instead of the disk, we will be able to query it much faster. Okay, so let's get some nuances of this flush that we are doing on the disk. Because it is not actually happening all at once, there is some steps in it. The data actually gets written into chunk files which are memory mapped. So let's imagine this is the head we have in memory. Now we will also have some chunk lengths. So let's say the total in-memory data we can hold is for 2 hours, and we will consider something called a chunk length for every 100 data samples, which will be, let's say, around 24 minutes. So in this 2 hours of data, there will be 5 chunks. So in this block that will be written on the disk, there will be 5 chunks. And the data is actually written in some chunk files. I will come to this. How is it happening, right? So what happens is that when one chunk fills up in the head, that is written in some files, and these are the files in the block. So you will see this structure that I've mentioned here is actually the files on the disk. Now all these files do not exist from first only. Chunks files will be started to be getting written at in the disk when the chunks in the head will start filling, right? So what will happen is when a chunk fills up, it will be written to whatever chunk file we are currently writing to. So let's say we will say that each chunk file will be of maximum 128 MB. So we will start with the first chunk file. So when we get one chunk worth of data in the head, we will write it in the current chunk file that we have, right? But when that chunk file reaches 128 MB, we will start writing the chunk data to a new file. So it's not like one chunk will be only written to one file. There can be multiple chunks in one file, right? Let's get that clear, right? But now you will think that, okay, we should have ideally kept all the data, all the 2 hours worth of data in memory. Why are we writing it, right? So we will pull out a neat trick here. It is something called mmap or memory map files. So these chunk files will be memory mapped to our program, which means that our program will actually see all this data as some in-memory data structure. For it will be something like a byte array. But the OS will take care of taking the data and writing it to the disk. So here your disk will act like some kind of a virtual memory to you. When there will be a lot of memory expendable for the operating system, it will be used to keep all your data pieces, or in operating system lingo, pages in the memory. But if you don't have enough memory, then also you will be able to treat it as if it is in memory, but actually the OS will take that data and keep writing it in the disk, and whenever you request some piece of data, the OS will bring that page to your memory, right? But if you have enough memory, I think then the OS will just keep everything in memory and do the writes also if you update the data, right? So this is mmap or memory mapping. I didn't go into very depth of how it exactly works, but this is kind of an overview. Now I should mention here that not all databases like memory map. Like for another time series database storage engine I was talking about, InfluxDB IOX, they don't use mmap. Many databases have the opinion that managing pages from and to the disk is better managed by the database itself than the operating system, and most of the times that's also a very good design. So the data will keep coming and we will write the chunks on the disk. So you will also see this chunks head folder. These files will be actually the ones helping the program to memory map the data in this chunks file. Now when the block has a required number of chunks, it is finalized on the disk, and this whole block structure that I have mentioned as the whole structure is created. Now our aim will be to understand what all these files are and what all these folders are, and how it exactly works, so that we'll have a nice idea of how this storage is done. Now let me give you some idea of how this chunks file is actually there. Like, I'll not go into very depth, but well, let me give an idea. So this is actually formatted like there are series of time series data written in it. What is one series? One series is basically the name of the metric and all these paths combined. So this is like, they put it like a combined string, you can consider it like that, and then all the data points that has come for this. So that is known as a series in tsdb. Why I'm mentioning this is because when understanding indexing, this will come into picture. One more thing that I should mention is that the data when written into these chunk files are encoded using various techniques to keep these sizes of these files small and saving our precious costly disk space, right? Okay, let's keep moving and we will investigate the anatomy of these blocks by going one by one, right? Okay, let's come to this part of the write ahead log. We are smartly keeping things in memory for some time because we know we can access it faster. But what happens if the database goes down? It will take all the data it has in memory down with it. To prevent this, in the block, we have something called a write ahead log or a wall. Whenever we are writing some data in memory, or any data is coming in, we'll always leave an imprint of this data in the wall. Basically, in the wall, we will be adding the operations that we are doing to the database, like adding a value, removing a value, so on and so forth. So if the DB goes down, we can use these operations, because these are persisted on the disk, to again rebuild our data and recreate our database at the same state. Now, because these are append only operations in these files, these write operations are generally very fast. Now, this write ahead log is a very common pattern that you will be seeing in many databases for recovery purposes. So this pattern is very important for you to know when you are building something of your own. Now you can see in this file structure, there are multiple files in the WAL folder, wall folder, because as in chunk files, all these files have a maximum size limit. After that limit overflows, new files are created and written. Now you will also see this checkpoint folder. So this means all the operations in the wall files till this point are accumulated in these files in the folder. So let's say there is an operation to add data, and for the same time range, there is another operation to delete it. We would not mention both the operations in this checkpoint because both of them cancel each other out. So when we have a checkpoint, we actually save space on the disk, and there are, I think, some other techniques too to make this space even smaller. So when we have a checkpoint till number 3, we can actually delete the older WL files, right? So let's imagine we had file 0, file 2 and file 3. When we had made a checkpoint of till 0.3, this means this will contain all the data from all of this. Now we can delete these files, right? So this comes the concept of the write ahead log, which we'll use for our database recovery. Cool. Now let's move further in our understanding of the data layout in the disk. You will see this Tombstone file. What is this? This is the record of the data points that are being deleted. We know that these chunk files cannot be touched once they are written. So these blocks you will see on the disk, these are immutable blocks. Once these chunk files are written, once this write ahead logs are written, these files are not changed anymore. That's called immutability. So we cannot go ahead and change these chunk files and delete the time ranges that we want to delete from them. But we'll have a separate file called Tombstone to mark the deletions of that time range data, right? So Tombstone is the file where the data comes to die. Next comes the meta.json files. So what is this? In tsdb, this meta.json files actually contains the metadata of the block. So that means metadata like the min timestamp and the max timestamp. There are some other metadata also which I forgot about. One thing that it is a human readable format in JSON. Also, it will be very easy to understand which block contains which time range of data, right? At this point, we have to discuss how the reading in this database would work. And I will come to this last file in the database index regarding that only. But let's first talk about the read flow. So whenever we get a query, we'll get a query like this. We'll get the metric name, we'll get the tag we want to search for, and we'll get the time range, right? This is how tsdb queries will be given to us. So I don't mean this is the correct syntax for a Prometheus query. I'm just using it for representational purposes, right? Okay, so what we'll have to do here is we'll have to do filtering on two things. One is the time range, right? This time range, and the other is this tag, right? And we'll try to see how we can do this very efficiently. Okay, so whenever the request first comes to us, first we'll search in our in-memory data. We'll first search in the head if we already have this time range, right? Then if we get it, we can just filter out the time range, filter out all the metrics that we got based on this tag, and then we can return the data. This will be very fast because all the data is in memory. But what if the data is not in the memory? Then we will have to search which block contains this time range first, right? Okay. So because the blocks are monotonically increasing, we can even do a binary search kind of thing. But let's say we find that this block 2 has this time range of data, right? Now we'll have to go inside block 2 and understand where I can get the data for this tag, right? So let's see what happens inside it. Now let's come to our index file. So the index file contains the places where we will find these tags. So currently we need tag for method equals to get, right? So this contains, the index file steals an idea from full text search databases like Elasticsearch, and it is called an inverted index. What does inverted index do? It will tell me where my data is for a particular token or for a particular tag in our case, right? So we will have method equals get and method equals post, right? Now I'll not going into the exact format of how the index file is implemented. You can read about it in the links I'll give in the description, but it is interesting by itself, so you can read about it, right? But let me give you an overview how this works. So this inverted index will tell us in which places in the chunk files will the series exist which has the tag called get. So there might be multiple series in multiple chunk files with this data. So it will list down all the points in all the chunk files which will have this data. So it will be like, you know, the pointers to those points on these files on the disk, right? So let's say I want the data of get. I'll search my inverted index. I'll take this, and I know that in this file at some offset I have my data, right? We will read that data and we'll only take the time range that we need. And if you will see in the post, I have given two arrows to these two files. That means for method equals post, in both these files some data exists corresponding to this tag, right? So it's a very simple way of doing this indexing, but it is at the same time very effective. The only problem with this indexing, you might notice, is that we actually limit ourselves in the number of tags we use, because all the tags will have to be individually mentioned in the inverted index, and their pointers will be going to the chunk files. This gives us some boundaries on the number of tags we can have, because it cannot be too much, because then we'll have to list all of it, and then it will be a hassle in itself to search the index. So for having more number of tags, systems like InfluxDB IOX actually uses Parquet files. If you don't know about them, it's okay. It's just a file to store tabular data, which can store a lot of tags as columns inside the tables. Another problem you will notice with our overall architecture that it does not provide separation of compute and storage, right? With with the separation of compute and storage, we can actually scale compute and storage separately, which means that if I need more disk space for my database, I'll not actually have to buy one more node of that database to keep that data. I can simply provision more space in my S3 buckets. And systems like InfluxDB, IOX are actually letting us do this. It can keep all its data in cloud storage like S3 and Azure Blob Storage, right? So you will actually see that it's not like tsdb is bad in this case and influx is good. It is actually very different use cases for both of this. InfluxDB is written for analytics use cases, so we need all this, and tsdb in Prometheus is focused on metrics and observability. So we can see that for two different use cases we have different architectures, which is fine. Okay, now we see that we have got a hold of all the files and all the folders that will be in the block. We know about the chunks, we know about the index, meta.json, tombstones, chunk set, and the write ahead lock, right? So we are done with understanding how the block will look on the disk, how the data will be written, and everything. We also know how to read from this data efficiently. The only small thing that is remaining to be understood is called compaction. See, opening a large file is better than opening multiple small files, because we have to track all those small files with their file descriptors across the disk. It's also better to read data in chunks rather than from multiple places, right? So there is this background process called compaction, which actually takes multiple blocks. So this is block 1, block 2, and block 3. It will create a new block, block 4, with the data of all these blocks combined into one block. The deletions marked in the Tombstone files are also now actually removed from the data, which will be kept in block 4. So it's actually also giving us space advantages, and the data will also be easier to search, right? But obviously there will be limits on the maximum size a block can go up to, and in the block force meta.json, it will be stored which blocks it has come from. So block 4 will store that it has come from block 1, block 2, and block 3, right? Okay, so this is all actually I wanted to talk about. This gives you an overview of how a time series storage engine can be designed. Now make sure to read the blogs I mentioned in the description to dive deeper, and also take a look at some of the code from tsdb, and I'll also share another blog post in the link with who have implemented their own time series storage. Make sure to read that code also, right? And one more advice, you can try implementing all these things by your own also, or maybe some parts of it. You will actually get very deep understanding than watching a video when you do things by yourself, right? So you should actually share this video with your friends, and leave a like in this video. Even if you don't like it, I don't care. And subscribe to the channel, because it costs you nothing. Just subscribe it, right? Help me to reach more viewers, and I will see you in the next one. Bye.